In this problem, I want to show you a really interesting little application that is going to require quite a bit of pure Python work, and it's going to show us a little bit of how we balance some of the work that we do in NumPy, some of the work we do in Pandas, and some of the work we do in pure Python. Let's take a look. I'm given a numpy.ndarray, and that numpy.ndarray represents some physical entities, some asteroids, which I'm going to assume, for the purpose of simplicity, are perfectly spherical. These asteroids have different radiuses or different diameters, and they're floating around in three-dimensional space because, after all, I'm stuck in the game, asteroids, I'm the little ship in the middle, and I have to shoot them down. Now, setting aside some of the mechanics of that game, I have modeled the position of these asteroids and their velocities. And I'm going to say that as a very simple model of the very first version of the game, I want to simulate what happens when these asteroids move around, maybe with some simulator that works every tick, and maybe where one tick is 1 second, and where when two asteroids collide, they mutually annihilate. My goal is to simulate this situation for some number of steps here until we're at 10 seconds. Let's take a look and see what we can do. Here is our underlying data set. And so we have some named entities. For each entity, we know what its position is at a starting point and what its velocity is at the starting point. We might even want to preserve this over time so we can do some analysis to see what the trajectory of these things are. If, for example, we then want to do some sort of inelastic collisions or something like that. And we have the size of each of these asteroids. Here, the radius of them. And you can see this one's a really big one, and these two are relatively small. And we want to simulate this as we go. Now, one thing that we do know is it's often the case that when we're performing a simulation, there are aspects of the simulation which cannot be encoded easily in the restricted computation domain. We also know that oftentimes when we're performing some simulation, there are parts of the simulation that are purely computational that we do want to stick in the restricted computation domain, and parts of this that just are slow enough that we want to be able to model in pure Python. And so let's take a look at a little bit of background in theory related to the ideas of eagerness and laziness. We know that in pure Python, we have two different ways to model a computation, either as an eager computation or as a lazy computation. A function is a simple eager computation, and a generator is a simple lazy computation. An eager computation is a computation which does work before you ask for it. And a lazy computation only does work when you ask for it. And so largely the difference here is whenever we're using a tool like NumPy or Pandas, and we ask, for example, say we have a numpy.ndarray, and in this numpy.ndarray, maybe we're representing some evolving process. So maybe we have the deltas. We do something like this. Let's get our random number generator. Let's get some integers like this. Maybe this is the evolution of some process. These are the individual changes. And to represent the state, maybe that's not too difficult. Say we have 100 steps in this. We'll just do a cumulative sum on that. So there we go. We get the state. And maybe, for the purpose of our analysis, once we hit a particular mark, like for example, once we get over the value 50, maybe the process terminates because it's not able to satisfy what happens when that value gets too high. And so here you can see we've simulated out a little bit too far because probably after this point, the simulation should stop. But fundamentally, NumPy is an eager tool. And so the approach that we take in NumPy is we just compute a bunch of stuff and then we do some sort of filtering to filter ourselves down to cases where we can use this data. So here we might do something like this. We'll look for the absolute value of this is less than 50. Okay, very good. And then what we want is we want the first place where that's no longer true. So that'll be a numpy zeros, I believe. No, it's a numpy, what is it? Here it's, I believe, zeros like this. No, it's roots. We want to find the roots of this thing? Yeah. No, not roots. Let me think. Find zero. So here it is non-zeros, what I think we want to do. Non-zero, and we'll non-zero like that. Okay, very good. What does this give us? That gives us whether each of these values, gives us every location where the value is non-zero. So what we'll do is we'll say it's greater than that, and that's each location where the value is non-zero. And then that gives us the first location where it's non-zero, and then we'll just slice to that location. So here you can see we have the evolution of the process up to, but no further than when the value is greater than or less than, or greater than 50 in the absolute value, in the magnitude. And we did a lot of extra work because we actually did a lot of computations here as part of this cumulative sum that generated a bunch of stuff we threw away. But it's okay. It's an eager tool. We eagerly do a bunch of work before we ask for it, and then we do some filtering down. And the general benchmark that we have when we look at these different approaches, the eager approach and the lazy approach, is if we consider the time it takes to do a single computation and the time it takes to decide whether to do the next computation, we generally see two regimes here. If the time for the computation is significantly less than the time for the decision, then the eager tool is in fact what we want to do. Because if we go back to this example and we say, here this represented some simulation and we ran it for 1,000 steps just in case, and then we did our cumulative sum to represent what the actual underlying state looks like from these deltas, and then we filter it down to how long the entity actually existed, because our rules say that it can never be larger than positive 50 or smaller than negative 50. Well, we ended up computing a bunch of redundant stuff. But the underlying incremental computation was incredibly fast. The cumulative sum, incredibly fast in NumPy. Even the creation of this random integer data, incredibly fast in NumPy. And so if it's the case that the computation is, say, on the order of nanoseconds of time, and the time to do a decision, to do something at the Python level in a for loop, which probably is about 1 microsecond of time, is significantly greater, then an eager computation is good enough. And in fact, I expect that we would need to have an enormously large data set here for this thing to be significantly slower than our pure Python approach, which would look something like this. Here we have the state, and we'd say for whatever or while true, state.append, a random number, and let's choose a random number uniformly. So let's do a rand range from -10 to +10 plus 1, like that. And then we do the state, and here we actually add this to whatever the previous value is. Here we'll see this with one value. And then we do something like if state of the last thing that we saw was greater than 50, break out of this loop. Something like that. And I'll just make this work for you. And let's get a random number generator there. And here, of course, this is a little bit too big for us to allocate, but and this should be like this. Here we go. To get the same general thing in pure Python, it's requiring that we drop into the pure Python level right here. And by the way, we should do this only if the value, just to make this exactly equivalent, we'd say if this last value plus the delta would be greater than 50, you break, otherwise you append. There you go. So you can see it runs up to, but no further than if the delta plus the state would be larger than whatever we have in here. And here this should be state minus 1 plus delta, just to make that consistent. There we go. So you can see it runs up to, but no greater than 50. Well, at every step along the way, the incremental computation, this addition, is going to be really fast, but the decision to keep going or not is going to be relatively slow. So it actually doesn't make sense for us to do this in pure Python. In fact, up to a fairly large size, probably makes sense for us to do this overly eagerly in NumPy and then just filter down. And here you can see, I suspect maybe around a couple 100 million, we'd actually see a meaningful slowdown. But even that, look how fast this is in just NumPy. This is so fast, 10 million elements. Whereas this Python loop to loop 10 million times, that's going to be quite slow. If the regime is in the opposite direction, the time for the computation is dramatically greater than the time for the decision. Again, maybe the computation takes a millisecond and the decision takes 1 microsecond. Then, instead of an eager computation, we want a lazy computation. This is our key to where pure Python and NumPy or pandas coexist. In other words, if the entities in your program have large aggregated computations that are slow, and by slow, what I mean is on the order of more than, say, a microsecond, because that's maybe our benchmark for how long it takes to run one line of Python code, one if-else in Python. So maybe on the order of more than a microsecond. Then we want to perform the raw computation inside, or one incremental, the raw incremental computation inside the restricted computation domain eagerly, and structure the combination or the sequence of computations outside the restricted computation domain in pure Python lazily. In other words, it is very common in our NumPy and Pandas code to see generators, but the generators should represent any simulation or process or solver that's not closed form, that cannot be pushed into the restricted computation domain, where the incremental computation is slow enough that we should just keep asking, should we keep going or not? In the case of something like this, we can imagine that actually might be the case for our problem. Because for our simulator, what does that look like? Well, our simulator takes the states and the info for our universe. And at each step, it needs to figure out what has collided, and it needs to update this structure. And so what it's going to do is it's going to decide what collides, and then it's going to remove the collided objects. And you can think in a later variation of this, we can even extend this, so maybe they break in half, whatever the case may be. But here we're going to mutually annihilate, we remove the collided objects, and then we loop. Well, the decision of what collides is probably going to be slow. Why? It's probably going to be slow because if we have 10 elements, they could potentially collide with any one of the other 10 elements. So from my thinking, there's 10 times 10, maybe 10 times 10 minus 1 checks that we have to do to see if we have mutual collisions. Well, even assuming that we don't necessarily have to check ourselves, still, from a time complexity perspective, this is going to be quadratic, which means that maybe 10 against 10, that's not going to be too bad. But if we have a million objects against a million, this is going to get quadratically slower and slower and slower. And this individual step is likely to be very slow. Even the trick that I'm about to show you will still leave this step relatively slow. It's just going to make it much faster. But structurally, what I probably want is some simulator that runs forever or runs while you still have entities. And so here there might be some check to see if everything was removed and then breaks, yields each step after deciding the collision and removing the entities. And that's the general structure. For deciding the collision, there is one very simple trick that I can employ to make this significantly more efficient. And that trick is the use of spatial subdivision algorithms. It turns out that I don't actually have to check everything against everything else. Because what I can do is I can say, if I were dealing with, say, a two-dimensional space, and I have some objects in two-dimensional space, here these represent my asteroids on some plane, what collisions do I have to really consider? Well, I have to consider the collisions of the things that are close. Well, is there a way that I can more cheaply consider what's close to what? Well, if these objects were uniformly distributed in this two-dimensional space, what I could do is I could break this space down into quadrants. And for every entity, I could identify what quadrant that entity is in. And then I could only consider the collisions if an entity is either on the boundary of the quadrants or within the quadrant, because there is no chance that an entity in the top left quadrant will collide with an entity in the bottom right. Only if it's on the boundary or if they're in the same quadrant do I have to consider this. And in fact, what you can think is this is a very simple subdivision of the space. What I'm going to do in two-dimensional space is I'll create what they call a quad tree. I'll take all the elements and I'll identify which quadrant they're in, and then I'll only consider collisions within that quadrant. Thus, if they're uniformly distributed, quartering the total amount of time that I need in order to determine how many collisions there were. If I'm in three-dimensional space and I'll have an oct tree, I'll just put this into octants, one for each one of the 1/8 of the space that I have. And if I'm using SciPy, I can do something even better. I can use a spatial subdivision algorithm, a KD tree. That's the second part to this. What I'm going to do is I'm going to take my raw data I'm going to put it into a KD tree and ask the KD tree to optimize identifying what could be a collision. And that's going to power making that incremental computation just a little bit faster, but still not fast enough that I might want to compute it eagerly, because ultimately there's no closed form for doing each one of these steps, and because the operation that you do for determining what happens when there's a collision could be arbitrarily complex, so there's really no way you can push all of this into the computation domain. So I'll still have some pure Python structuring. Let's take a look at the answer. So in order to answer this question, I'm going to first grab my raw data, and we'll take a look at my raw data. Here are my initial states, position and velocity, and here's my info, each element indexed on what its radius is. And so let's structure this kind of nicely. Let's put this in an if name equals main block, so we can show you which parts of this are maybe library code. Let's write a simulator, and the simulator will take the state at one point in time and the info. Let's make this an infinite loop, so this will run forever for now. Then what we'll do is we can't create new entities in this version of the game, so we don't have to update the info, we just have to update the state. So we'll decide the collisions, and given those collisions, we'll have some structure here that represents maybe the elements that are colliding. Maybe we have a Python set here. These are the elements that collided. We'll take the state, and we might make a copy of this, maybe an explicit copy of this, or actually, if we do a lock operation, it'll make an implicit copy, so that should be enough. So we can say something like the new state is the state. We'll pull out everything at its index, subtracting the collided objects, like that. And then we'll yield, and here we can just replace the original state here. So we'll yield the state. And just so that I make this complete, I might yield the state first, so I always have what the original state is, and then update it afterwards. And I think that's good. So here I'll move this to the top. I'll always yield the state at least once. Then I'll decide the collisions, and then I'll update the state, and maybe I'll decide. If we continue, I'll put a break here. I'll say if the state.size, or if the len of this thing is equal to 0, we'll break out of this loop. So I just have to decide the collisions. Okay, that's not too bad. Let's actually set this up. Let's have our simulator with our state and our info. Let's run one step through the simulator. And let's see. Simulate is what we called it. There we go. And let's take a look at what that next state gives us. That's going to give us the next state of this. And just to make our lives a little bit easier, we'll start with fewer entities in total. We'll just start with 3 entities in total. Make our life a little bit easier. Now, we need to decide the collisions and then make this work. And by the way, let's do 2 steps. Okay, so we can see nothing happened here. For deciding the collisions, what we'll do is we'll go into SciPy Spatial, and we'll pull out KD tree. And each step along the way, we'll create a KD tree from the positions. Okay? We'll ask this KD tree to query what are all the collisions, assuming that these are uniform balls. So each one of these points is a ball with a set radius. And so we'll just say, what are all of the collisions that you see, given the radiuses like this? And this should give you, let's just print this out. And we'll actually do this after, there. So you can see here, for these elements, there are no collisions. You can see for each one of these elements are by themselves. And if I make these elements a little bit larger, let's make them much larger, we should see more collisions. Okay, now you can see everything collides with everything else. And if I make them just a little bit bigger, you can see, okay, in one case they collide, but in other cases they don't collide. Now, I'm passing as the second argument the radius. So your collision is determined by your radius. So it's the case that this won't be symmetric. I might collide with you, but you didn't collide with me if I'm bigger than you are. Because your radius will cover my point, but my radius won't cover, or vice versa, my radius won't cover your point. So this gives us each one of the entities, and we'll do something like this. We'll get each one of these and the group of everything that was collided with, like this. So there we go. And here we go. This is what the collision was supposed to be. What we can do with this, just to double check that this is correct, we can ask for the iloc, because this gives us the indices of where each one of these are. So we can take a look at where the things that it thought collided were. Like that. So you can see that's where it thought the things that collided were. We could even compute what their distance is. So what we do is we would subtract these, and we'd square every entry. Then we'd sum this to get a simple Euclidean metric, and then we take the square root of that. So this would give us that would give us that. So that's the distance there. And obviously, we're going to filter out cases where if x equals y, continue. So we don't include self-collision. Okay, there we go. Nothing collides until we increase the radiuses a little bit more or increase the number of entities a little bit more. So there, everything collides, and you can see, okay, that's the distance. Those are all within our 20 radius. So this seems to be working. Very good. From this, we know that if there was a collision, then we mutually remove each one of the elements. So we could say collisions.add x and y, or add x, collisions.add y. Although what we probably want to do is we want to probably get the name here. So we're going to do state.iloc, or actually we can do state.index and just pull this right out of the index like that. State.index, pull that out of the index as well. So it removes both of those. Move that to the top. And then, as part of the transition, we're going to take the remaining elements, and we need to transition them based on their velocity. I believe that's just state of the position just gets added to its velocity. So this should give us the movement. And so, oh boy, one of these things is moving real fast. Let's see, yeah, because this is moving negative 6.5. So it went from here to here. And if I run this for 10 steps, then I get tick size of 1, 10 steps. And you can see, for this small number of elements, nothing collided. So let's see if we can increase the total number of elements and see if we can get some collisions in here and see if this thing runs. And you know what? Why don't I just say 4 step in the simulation, and we'll see how long the simulation runs until, oops, there's nothing left. Okay, very good. Oh, and they keep moving. So maybe we need to do some bounding box stuff because they keep moving in their path. And so maybe, you know, if this thing hits the end, the extents, then it needs to bounce off the extents or something like that. So we might say if, you know, state position, let's do one thing here. Let's put a single break here. And let's say if this thing gets larger than the extents, so we'll slice this just so we can see 2 steps. If the size, if any one of these, let's say state position greater than 10, look at the absolute value of these. So if it hits the bounding box, then it falls out of the arena. And here, let's do this. Let's pull this off very quickly. So there we go. And then here we'd say we do an any across the do an any across this axis. So here we're going to say axis equals columns. And then here this gives us one more set of things that we want to remove. So we can say, you know, prior to it, I guess we want to do this after it's moved. And so here we get the index of this thing. And we'd say state equals, and we'd actually filter this thing down. So we do something like loc lambda ss. So those are the things that also flew out of our range. We'll get the index of that. And we're actually going to remove those as well. Out of range. So that's the last thing we'd have to do to make this work. And we should see that everything eventually either flies out of range and is no longer able to be considered And let's just make sure that's good, that's good, that's good, that's good. We just got to put parentheses here. There we go. And now if we run this thing forever, we'll see either they collide and mutually annihilate, or they fly out of range. And let's remove our iSlice. So we run this thing forever. And we have a very nice, very simple little simulator. And by the way, one more thing, that's good. Remove that. That's state equals state.lock. That's fine. That's fine. Let's see where our problem is. It's here. And we want to remove those index elements and just double check what's going on here. State index difference. Let's see why. Once these things fall out of range, we gotta just see why. So there, that should be fine, that should be fine. And so one last piece here is there's probably one piece that we need to reconstruct this based off what the new state was. That's correct. And so the query ballpoint should be done against the original object. That's correct, having constructed this here. And so here, actually, I think we want to do this. I think we can do this against the same KD tree. No, that should be right. So I think we're close enough to work this down. We just have one small piece that we got to figure out, which is, oh, and the info. Here we have to update the info, so that's why. So here, info equals state info.lock state.index. That's why. There we go. And you can see here, we end up with just one element left, and our simulation worked, and you can see how these things might either collide or fall out of range.